Alright everyone, this next lecture in our series is going to be all about star formation. There's a lot of information to get to, so let's get started. So we know that stars are born in interstellar clouds, which are called a nebula. They're dark, they're cold, they don't have a lot going on in them. These clouds, once they get big enough, will begin to contract, and gravity will then begin to pull every particle and dust towards the center of the cloud, of the nebula. At the beginning of star formation, we have what's known as a protostar, and this lasts about 1,000,000 years. And a protostar is a very small star. It's relatively cool, and it's more red in color. Once the internal temperature reaches 10 million Kelvin, we have nuclear fusion begin. Remember, nuclear fusion is two hydrogen atoms, deuterium and tritium, combining to form helium. That's why hydrogen is one of the most abundant gases in the universe, second only to helium. So once a protostar gets big enough and gets older, it becomes a main sequence star. Main sequence stars have a lot of different characteristics to them. They can be a whole bunch of different colors and temperature. A hot blue star will deplete their hydrogen fuel in a few million years. It does not take that long for a blue star to burn up all of its energy. Think of it as speeding down a highway. The faster you go, the more fuel that you'll burn. And in this case, for stars, the hotter a star is, the less time it'll take to burn up and use all of its fuel. A yellow star, and yellow, we can't think of our star as a yellow star. That, when we look at it in the sky, it appears yellow, but that's only because of the scattering of light. In space, if you look at the sun, it's white. So our star is actually, the color is actually white. Yellow, in this case, is referring to the Hertzsprung-Russell diagram, which we'll get to in a minute. A yellow star, though, like our sun, will last for about 10 billion years, or about halfway through our lifespan of our sun. Red giants occur when a main sequence star, is nearing the end of its life. The outer atmosphere of the star will expand. These stars can become incredibly huge. Some of the largest stars in the universe, if you were to place it into our solar system, the outer atmosphere of it would extend past the orbit of Mars. White dwarfs, once a star has depleted all of its fuel, it will collapse under its own gravity and go supernova. Supernova is an exploding star. There's been recent developments in the news about the star Betelgeuse, which is the left shoulder of the Orion constellation, that it's starting to pulsate and kind of twinkle more, and they say that could be going supernova at any point in time. When a star goes supernova, the explosion that we see is brighter than the sun, so we would actually be able to see it in the daytime. The picture here to the right is a star that has gone supernova. That red and green is the atmosphere of the star that has been expelled outward, and the white dwarf, is in the very middle of that cloud. Sometimes a star will release its outer gas, like we see here, creating what's called a planetary nebula. So a neutron star is a very, very small, very, very massive star that remains after a supernova. It's really the center core of this star that's remaining. Some of the most massive neutron stars are smaller than some of our largest cities. A supernova occurs when the outer layer, like I just said, is ejected from the star, and the star will collapse in on itself. And then the next step would be a black hole, but we're not going to get into that right now. The Hertzsprung-Russell diagram is used to classify stars based on a bunch of different things. So a star's brightness, as it appears from Earth is the apparent magnitude. That is very, very important. It is the apparent magnitude, how it appears to us from Earth. A lot of people think the North Star is the brightest star in the sky. It is not. It's one of the faintest stars. The closest star to Earth, Proxima Centauri, is not the brightest star in the sky. It is actually Sirius. So, and that's it's in the Canis constellation. You know Sirius XM satellite radio. Sirius. There's the Sirius satellite radio logo is a dog. With the I think with a star as the eye, and that's where they got the logo, because Sirius is part of the Canis, the dog constellation. So apparent magnitude, how it appears to us from Earth. Oh, I did not want to do that. Let's go back there. There we go. Sorry everyone, give me 1 second. There we are. Okay, so there are 3 factors that determine or that go into the Hertzsprung-Russell diagram. How large it is, the actual size, how hot it is, the temperature, and the distance the star is from Earth. So the absolute magnitude is how bright the star actually is. 2 stars of the same absolute magnitude usually will not have the same apparent magnitude because one will be much, much further away from us. So think about that. That should make sense. 2 stars with the same absolute magnitude will not have the same apparent magnitude because one is further from Earth. Astronomers determine what magnitude the stars would have, the absolute magnitude, if they put it at a standard distance. So they put all the stars at a distance of 32.6 light years. I don't know where they got that number. I could find out, but I don't know at this time. And then they do some calculations, and that's where they get the absolute magnitude, putting the stars at a distance of 32 light years. And remember, a light year is the distance light travels in 1 year. So the sun has an apparent magnitude of negative 26.7. Okay. So the lower the number, the brighter the star would be. Obviously, the sun is going to have the lowest number at a negative 26.7, but an absolute magnitude of 5.0. So our sun is actually a very average star, average temperature, average brightness, and average size. The more negative, the brighter the star, the more positive, the dimmer the star. Okay, Sirius has a lot different numbers of apparent and absolute magnitude. Here is the Hertzsprung-Russell diagram. The right hand column, or the right y-axis, is the absolute magnitude. So you can see these supergiants and these blue stars are the brighter stars. Sirius is a blue star. It is incredibly bright. It is in the night sky right now. The main sequence, the yellow stars, that's where our sun is, kind of right next to the main sequence label there. And then towards the bottom right, those are protostars, very dim stars, and then white dwarfs are there as well. So that's a very quick introduction to Hertzsprung-Russell diagrams and star formation. There is an assignment for star brochure on the website and in Moodle, and that needs to be done by April 6th.